granules as the anode to provide a lot of surface area for the bacteria to grow. Currently, the cathode is just a stainless steel plate. And well, one of them is operated continuously, so it's being fed hydrolyzed urine from the urinal that you just used. I think. Thank you very much.
We dumped water and caffeine in it. I think very little nutrients.
And then these two were started more recently, so they're still in batch mode to get them to the same level as that one. And so one of the operational challenges that had been observed in previous lab scale systems was the accumulation of gas in the system as well, because as Stefano mentioned, acetate is oxidized to CO2 at the anode, the cathode is producing hydrogen, and previously the mixing was provided just by circulating the analyte and catalyte over a pump, but what we've now implemented are these phase separation columns, so simple bottles where the gas is actually allowed to come out, and that has been working nicely, so there hasn't been any gas accumulation issues in the system. That will be also done in the pilot, so maybe if you remember from the photos in my presentation, we have these tall, narrow columns that will be doing the gas separation for the anode and cathode.
So where is concentrated fertilizer? Where is concentrated one?
So it's produced in the middle chamber, and then it comes out through here. So basically, those ones would be the concentrate.
So this one is concentrated, okay.
Yeah. So
the other one is diluted one, right?
that's actually also concentrate, but from a different reactor.
So dilute is dumped out, right?
Yeah, this is the effluent. So yeah, that's the hydrolyzed urine. It goes in to the anode first, then through the cathode, and then from there it comes out, and it can go to the sewer.
So what was the concentration factor?
It has been around 3. Or it depends a bit. The concentration in the urine also varies a bit. Typically, what we've seen here is around 5 grams per liter, and in the concentrate, I've been getting up to around 19-20 grams per liter. So actually,
that's
up to 4.
from one pass, right? So is it possible to have a series?
Yes, actually, one of my our previous colleagues from UGOLD was looking into that kind of operation in series. Now I don't remember exactly what the findings were. Stefano might remember better, but there was, I think, it didn't work super efficiently, but I can't remember why. But someone looked into that.
So this one is.
So this is now the anode circulation loop.
Yes,
so I actually have these two hydraulically combined at the moment for the inoculation. I will then separate them later. But the analyte will circulate over this bottle, and the catholyte over this one. Similarly to that one, although it's anode and cathode.
So pH of this concentrate one
it's
is
around 8 point, typically above 8.5.
8.5.
So slightly lower than the original urine, but it's slightly basic.
Slightly, but still ammonia is a little bit producing, right? Because you don't control pH, and then ammonia will clean up.
I don't. So potentially some ammonia could be volatilizing.
Yeah.
Although in my PhD, when I was working with a different wastewater stream, I was also looking at ammonia stripping, and at least based on my experience, it was quite hard to strip the ammonia out of the liquid phase. So
I see.
Yeah, ideally all of this would be done in a fume hood, but
a
bit limited with fume hood space, plus I need to use the potentiostat, which is here and shared by other researchers.
Right.
So yeah, the smell is a bit of a nuisance.
I like smell.
Yeah.
I like it. I
After
like
working
it.
2
Yeah.
days in wastewater there.
Nice.
It grows on you.
Stefano love it.
Yeah.
So where do you measure your current density?
Color density.
Current density or current density?
Um,
Your electrical energy, how you
Oh,
measure that? Yeah.
Yes, so it's done by the potentiostat.
Okay, so it's connected here.
Yes,
or?
so those thick cables come from the potentiostat, and
Yeah.
then I'm.
Okay.
So this is now a 3 electrode setup. So the
Yeah.
anode, cathode, and then there's a reference electrode. So I'm currently controlling the anode potential to provide suitable conditions for the
Okay.
microbes because they like a specific.
So
potential
this is the
range.
real. This is potent state,
Yeah,
right?
the blue.
Three of them is connected.
Yes,
Yeah, all of
correct.
them.
And so I'm applying a potential, and then that will record to the
I
current
see.
and the power of the counter electrode
All right.
or the cell voltage, basically.
What's the highest concentration you have achieved from your
It's been around 20 grams per liter.
20 grams? How about maximum? How much you can do? 20 gram is only 2 times. Like let's say hydroiodine 10 gram. Yeah, 10 gram.
Yeah, well, what we've been seeing is this is typically around 5 grams per liter.
Yeah,
to
5
start
gram,
with,
okay.
So it's been around
4
like a
times.
4-time concentration. It's been in some previous lab work, I think the maximum has been around 25 grams per liter. So
25.
It's, yeah.
So you need to
typically
further
all-
concentrate, or just to use as it is 25 gram per
That's
liter?
maybe a good question as well. I mean,
That-
it is still quite dilute compared to.
All right, it's 25. Yeah.
Yeah.
Of course,
commercial
it's
fertilizers.
yeah.
It depends. Also depends on the distance it would need to be transported. Of course, if we're producing it at the park in Brisbane and they can use it locally within the park,
Yes.
might not be a problem.
Okay.
But
Nice.
yeah, definitely a valid question.
Yeah.
I can see still a lot of turbidity is inside, even though it's ion exchange membrane pass-through, right? Concentrate one. This looks like still
that one-
turbidity is there, right?
Yeah,
Is
I
it?
think that one has been having some hydraulic issues around it.
Is it just
as
okay?
well, 'cause
Because
So
I
when
I
the
expect.
concentration goes above 20 grams per liter nitrogen, then you have no longer turbidity because
No
the
longer.
bacteria cannot grow.
Oh, so still because of
that-
bacteria there, right?
So yeah, so
The
this-
microorganism.
you're not working that way yet, right?
Yeah, no, it's still below 15 for that.
I see.
So it's really critical to reach high concentration to avoid growth. Otherwise, we can't sell something that's got bacteria in it. When it was exposed to urine, it needs to be properly biocidal, and for that, it needs to rise above 2% ammonium nitrogen. So that's the tricky bit. For electrodialysis, we also although it works quite efficiently and stable, the concentration factor is not better than this. It's limited by osmosis and electrosmosis, so you can work around those, but at optimal conditions, we've got 25 grams per liter of ammonium nitrogen. And if it drops below that optimal level, then quickly you can have a product that is not appealing anymore.
I see.
So that's why the new student, I want to try direct electrolysis.
Okay.
So basically, instead of
Yeah.
evaporation, convert the water into hydrogen and oxygen, and that way concentrate. And obviously there's going to be issue with chlorine, but I don't believe there will be big issues with fouling and scaling because of the biocidal conditions and because we don't have any calcium and magnesium after the hydrolysis process.
Okay. So membrane is from where? Is it from AJJ technology they provide
These are
or?
bought from US,
Yes.
Membrane International, because
International.
they're very sturdy and resistant to high pH.
Okay.
So we've been using them for years, and we haven't found one that performs as well as these ones for urine in terms of stability. So ideally, we'd like to find something that works so well, but also has a bit less water coming through. So lowering the osmotic and electrosmotic. And electrosmotic is very hard because if the ion goes through, it goes through with water. But for osmosis, it could probably different membrane formulation might help with that. But I think electrosmosis is really the main component of the water flux.
Okay. So one square meter of membrane can produce what's the flux you are producing? Like LMH, we just say.
Well, so
Okay, this size level.
So it really depends on the current density that you apply. Because,
Right.
So here at the current densities, you know it off the top of your head?
No, I don't.
So, but so for like 30 amp square meter, you were feeding how much per day per reactor?
I haven't really got up to 30. I was supposed to be like 15.
So
That would be around 2 liters per day.
2 liters per day means roughly 0.2 liters. We know a rule of thumb 10% goes through. So 0.2 liters per day. This is 100 square centimeters.
200.
200.
Yeah.
200
So
square centimeters.
so
0.2,
200 milliliters.
0.2.
200 square centimeters. So 1 milliliter per square centimeter per day. So if you want LMH, so 0.2 liter. So now we say so 1 milliliter per square centimeter per day. Now we have to do 3 conversions. So 1 milliliter. So divide by 1,000 square centimeters to square meters. There's 10,000. So multiply by 10,000 square centimeters per square. So multiply by 10. So, and then hours to minutes. Now day to hour. 24 hour per day. So multiply by 10 divided by 24 is divided by 2. So it's about 0.4 LMH. So
It's very, very low, yeah?
if you're looking at it
0.4.
from LMH point of view,
yes.
but really we want to reduce the LMH. We want less water. It's really because it's electrodialysis. We want more nutrients and less water. So we are happy with low LMH if the nutrient flux is high. Because this is electrodialysis, not RO.
No, yeah.
So
What say if because it generates energy, if you can run something else from here, does it like
this consumes all the energy it generates.
itself, right?
Yeah.
It itself.
Because that electricity is needed to run the electrodialysis process.
So how does it produces then go to the external one and then put it inside, or how does it work? Because this energy is generated in situ, right?
In situ. So directly it's electron flow. So the bacteria generate electrons, and the electrons are just going around and generating the voltage.
So it doesn't have to go out and then come back to feed in.
No.
So it's used within that. So which means if you want to trap the energy source, you can't because it is within that system.
Yeah. I mean, you have to do So if you're interested in energy only, then you would run it at open circuit and feed it with the urine, let the bacteria absorb the organic matter and charge up, and then discharge it. And then you might get really high current density for a short time. It's something that could be interesting to look at. Particularly when we're looking at electrodialysis on a solar panel. If we don't want to put the battery in, then could this provide the ability to store the energy? So it's potentially a form of energy storage. We haven't fully assessed how much energy these systems can store. It's really the storage of organic polymers in the bacteria. So, and also whether, like, by applying reverse voltage, whether we actually induce more storage, which then would allow the bacteria to be more charged up. So this could be interesting research questions.
So what's your best scenario? Okay, let's say you want to install this one in Brisbane public toilet. The best scenario, okay, well, hydrourine goes to your technology and how much you want to concentrate, and then you directly apply in the parklands as a diluted.
So
what's the
ideally, so when this one works well, the urine is hydrolyzed in a tank, so you don't have any calcium and magnesium. It comes into this fed continuously, and at optimal condition we'll get enough concentration that the fertilizer product is clear, so no growth, and strongly ammoniacal, so full ammonia.
Yes.
And that product to be mixed with water for fertigation and of the local flowers and horticulture. So there would be a 6 by 6 meter garden right in front, where there will be plants displayed that are grown on this fertilizer.
So your final concentration of this technology will be around 20 or 30 gram per liter?
Yeah, we never reached 30. 27 was the max.
27, okay.
20 is typical. 25 would be ideal, because we know that at 25 there's nothing growing there.
So, okay, so you have to balance that carefully. Yeah, if you have too much fertilizer, you cannot utilize it, right?
Yeah, we have a column to accumulate fertilizer, and if it's too much, it overflows into the sewer. But then anyone can come and open the tap at the bottom and fill their own bottles and take it back for their own experiments.
Nice. Yeah.
So really nice and impressive, because we have now these are circulation bottles. You can't see much, but those ones are nice and big, and so we'll be able to see through all the fluid that comes through, and on the cathode side there will be you can see all the hydrogen that is coming out.
All right. So this is already ready for the pilot. Now it's I do remember you gave us a very heavy stainless module.
Oh, that
you
one,
remember? Yeah.
So that is one cell of the ones that but it seems like the pilot, which has 10 of them, is lighter than the one you got. Because
you gave her like
I think we made the materials thinner, like we optimized a bit, and that was the first prototype.
Nice.
So you got for one cell something very heavy. In Sydney, there is the prototype of the pilot cell, but with its own plates, which are stainless steel and therefore extremely heavy for just
I think it's aluminum.
for just a 3-compartment cell.
I think that because there are no pressure or not much, harsh conditions, so you can use acrylic as it is like a big scale, right? You don't need like a standard. You don't need a very
Yeah,
heavy.
absolutely, absolutely. I mean,
Yeah, to make sure that it doesn't leak. It's okay.
How about when you operate maybe several months? So like electrode, you may have a poison or some scaling or some. Do you need like a cleaning
We-
procedure or
these ones have been going for a year
doesn't
without
matter?
any trouble. The
Okay.
anode is biological and
Yes.
it replenishes itself.
Uh-huh.
Dead cells detach, new cells are born.
Uh-huh. But the dead cell can be attached continuously, like some scaling, organic, or whatever,
The problem is if you stop feeding, then they die and they form a crust on top, then it's the end.
Yeah.
If you keep feeding, it grows from the inside, so from the granule, but the film grows and then the outer cell, they come off. So there's no trouble with that. The cathode is purely a stainless steel plate that makes hydrogen. Because of the conditions, you don't have much biofouling because it's pH 9 and it's got ammonia. Never had a problem. The membranes, they do get some fouling, but it doesn't seem to impact our energy requirements so much. So it is a kind of like a
So you don't need a chemical cleaning, you don't need
yeah.
any extra.
For 1 year,
Yeah,
no problem.
1 year no problem. Yeah? How about 2 years?
Well, in the pilot, unfortunately, we were going to run it for 3 years,
Yeah.
then it becomes 2, and now it's 1.
Uh-huh.
Because they keep postponing.
Right, okay.
We're waiting for the outcome
yeah.
tomorrow.
No, we can extend your project.
Well, but you need to pay
You'll
for
have to
Vera.
pay
Okay.
me.
So now, yeah, all the money is going to Vera's salary,
I know.
and the pilot is
She
gonna,
can apply for Vice Chancellor postdoc.
she can. Yes. Now because until last year it was only for external, but there was two scholarships, 2 fellowships,
I know it's
the external
very
and the
tough, yes,
internal.
yes.
Now they combine them.
I see. So it's very impressive. Yeah. Do you have any, our MBR, we are going through the exemption of the resource recovery from EPA. Do you have to do that kind of thing? Like you need to prove consistent?
Because this is the Queensland node.
Yeah.
In Brisbane, we already talked with the regulator from the beginning, and they say you need the permit only if you produce 100 tons per year, something like that. So for anything small, you don't need any permit. And then if it gets big enough, then you need to apply for a permit. But that's called a end of waste permit. So basically, the same thing that allows you to recycle wastewater on land. So treated wastewater on land. So end of waste permit for assessment of its safety for land application. So for fertilizer, that's where we haven't found that there is a particular regulation to constrain what can be called a fertilizer. But
that we have half of the project now, and then next year, it's almost 30 time to thinking about next step. So possibly we also thinking about the New South Wales, like SME funding, small and medium-sized business. There are several nowadays, a lot of opportunities to get scale up or maybe TRL 5 or 6 funding opportunity. So we are also thinking about our MBR technology for the more TRL high-end and commercial level of the application. So possibly you can also think about, of course, the New South Wales, even Victoria, even Brisbane, for the more higher TLN, and you can get more funding and then more, because already you have a established commercial level of the scale of protocol. So that could be, we can think about now is what we have progress is very fantastic, and then now go for the more funding for the scale up. So maybe from next year we need to think about like how we can get more funding and then support our PhD student for poster or poster, that could be.
Definitely we'll have to think about.
Also, we are thinking about how we can get this one.
Is it double layered or like
Yeah.